Hi, I am David Delmas from Airbus, and I'm going to talk about our work on static analysis of Endian portability. This is joint work with Abdelraouf Wadjaout and Antoine Minet. A word on Endianness first. There is no consensus on the representation of a multi-byte scalar value in computer memory. Little Endian systems store the least significant byte at the lowest address, while big Endian systems do the opposite. Little Endians include Intel processors, while big-endians include Internet protocols and legacy or embedded processors such as Spark or PowerPC. Note that such conflicts might trigger religious wars, such as the civil war Gulliver witnessed when traveling to the land of Lilliput. There, he met little Indians who insisted that eggs should be broken at the little end and fought big Indians who wanted to do the opposite. Endianness is an important source of portability errors, especially in the case of low-level C programs. Indeed, the C standard leaves the precise encoding of scalars partly unspecified. As a consequence, the same source code might behave differently when run on platforms of opposite Endianness. Therefore, porting existing software to a new platform with opposite Endianness can be quite challenging. Let us show this on an example. Here, we have a small program originally written for a big-endian platform. It reads a 2-byte integer into variable x, copies x to y, and then reads y using the big-endian convention. The value is 1. Now what happens if we run the same program on a little Endian platform? Well, we get the same bytes, but when reading y with the little Endian convention, we get a different value. Now if we would like the same value, we have to change the code, replacing this assignment here with a byte swap. So we read the bytes into x, byte swap x into y, and read y using the little Endian convention, and we get the same value as with the big Endian program. Now, if we merge the two program versions using conditional inclusion directives, we get a so-called Endian portable program, which ensures that both program versions read the same value for y. Note that there are other ways to byte swap x into y, such as bitwise arithmetics. This is extensively discussed in the paper, but skipped in the talk. We want to do Endian portability analysis. A program is called Endian portable if two Endian-specific versions thereof compute equal outputs when run on equal inputs on their respective platforms. In this talk, we present a static analysis able to infer the portability of large real-world low-level C programs. After the motivating example, let us describe the syntax and semantics of the language. As we may have two versions of the same programs, we deal with so-called double programs, which are composed of double statements, which can be simple C-like statements or pairs of statements. The parallel sign here denotes syntactic difference, such as differences introduced by conditional inclusion directives. Note that even when both program versions share the same statements, the semantics might be different, as assignments, for instance, do not write to memory in the same way. Simple statements are C-like statements where all left values are assumed to have been preprocessed to scalar dereferences. Scalar types include integer types and pointers. Expressions support pointer arithmetics at the level of bytes and non-deterministic choice. There are also additional statements, such as the assert sync statement here, which says that both program versions agree on the value of the expression. Now, to define the semantics of such double programs, we simply lift simple program semantics. Simple memory states are standard stores from variable to values. Double memory states are pairs of such stores. The first element of the pair represents the little Endian memory, and the second element, the big Endian memory. The semantics for double statement S takes as input a set of double memories and returns as an output the set of possible double memories after running statement S in both program versions. To formalize the transfer functions, we leverage previous work on patch analysis. In the case of two syntactically different statements, the semantics is simply pairing the semantics of individual statements, such as computed in their respective environments. The case of tests is a bit more involved. It uses the F filter here to distinguish between cases where both program versions agree on the value of the controlling expressions and cases where they do not. The first two cases are stable tests, and they're standard. The two last cases are unstable tests. In this case, for instance, we compose the little endian version of the then branch, filtered by the condition, with the big endian version of the else branch, filtered by the negation of the condition. And this is the dual case. The semantic of the asserting statement simply filters away any double memories which might disagree on the value of expression E. In this case, an alarm is raised. It is not displayed here for conciseness. Then, to define the semantics of further statement, we simply do by standard induction on the syntax. Yet, we still need to define how memory is accessed for reads and writes. And for this, we need a memory model. At the most concrete level, each program version holds values for individual bytes. Yet, we deal with C programs, which have multi-byte access to memory, and we want to compute numerical invariance. Hence the need for scalar cells, which are synthetic scalar variables holding values for memory dereferences. In addition, we want to deal with low-level C programs, which tend to abuse the weak type system of C with unions and pointers to get byte-level access to the encoding of scalars. As a consequence, cells might overlap. We therefore view memory as a dynamic collection of cells holding values for memory dereferences discovered during the analysis. More precisely, a cell is a tuple with a base variable, an offset, a scalar type, an Endianness encoding, and a side, little endian version, big endian version. With such a memory model and any standard numerical domain, we may define a static analysis using one dimension per cell. Let us do it on the example. Here we have the little endian memory, here we have the big endian memory. When we write the same values to the bytes of X, we synthesize these cells, these 1-byte cells, in both memories and record equalities in the numerical domain. Then we byte swap X into Y in the little endian memory, which creates these cells. Then we read X in the big endian memory, which creates this cell from the values of overlapping 1-byte cells. Then we assign X to Y, which creates this cell. Finally, we read Y, which creates Y1, as we already have Y2. And then we query the numerical domain for equality. Equality can indeed be proved from the program invariants and cell constraints that we have inferred. Yet, these invariants are quite complex and would require powerful domains such as polyhedra. And this is not an option as we plan to scale to large real-world program. Fortunately, we notice that most invariants are equalities, and most such equalities are between the little endian version and the big endian version of the same cells. And this is not a surprise, as we expect in a portable program that most multi-byte cells will hold equal values in both memories. We thus optimize our memory model for this common case, and we do this by sharing cells in the memory environment. We want a single representation for two cells coming from different program versions at the same memory location and holding equal values. We thus define B cells to be either a cell or a pair of cells holding equal values, which we call a shared B cell. Let us recall the analysis of the example with cells. We had a lot of pressure on the numerical domain here, and when reading variable y, we had to synthesize cells y1 and y2 and then query the numerical domain for equality. Now, when moving on to B cells, we first merge the representations for memories here. We reduce the burden of the numerical domain by synthesizing shared B cells for the bytes of X when the same values are written to these bytes. And then, when reading Y, the memory domain does not immediately try to synthesize Y1. It first tries to synthesize a shared B cell for Y1 and Y2 instead. And the way it does it is by looking at a number of possible patterns, such as the following. It looks in the memory environment for any existing cell which would be equal to both Y1 and Y2. X2 is a candidate because we have this equality. Then it looks for overlapping 1 by cells for X2 and Y1, and queries for equalities. And as X2 and Y1 have opposite endianness encoding, it queries exactly for these equalities. Here, the success of shared B-cell synthesis relies on this abstract pattern matching and on a set of equalities which can be inferred with simple symbolic propagation or a full equality domain. Now, we have implemented our work on the MOPSAT platform, which allows for modular development of precise static analysis for multiple languages and multiple properties. Our prototype is 3,000 lines of OCaml, most of which for the memory domain, and it leverages much more code of the platform. We have experimented our prototype on open source and industrial software. We have chosen open source software projects available on GitHub with multiple patches related to Endian portability bugs. We analyze small slices thereof using our specification primitives. We're able to find all reported Endian portability bugs and also to prove Endian portability where applicable. We also analyzed two components of a large prototype avionics application developed at Airbus. This application is designed to run on an embedded big-endian platform. Nonetheless, these two components here are designed to be portable to Little Endian, as they are also to be integrated into a simulator which runs on a Little Endian platform. We analyzed these two large code bases quite precisely with no false alarm related to Endian portability. Note that the analysis of module A was performed before its first integration into the simulator, and all findings have been incorporated into the development cycle. As a consequence, the simulation team were faced with zero Endian portability issue when integrating module A into their simulator for the first time. To conclude, we have presented a static analysis of Endian portability based on a novel concrete collecting semantics able to relate the behaviors of two versions of a program executing on platforms with different endianness. It is based on a joint memory abstraction able to infer relations between Little Endian and Big Endian memories. We have implemented a prototype static analyzer able to scale to large industrial software with no false alarms. In the paper, we also present the symbolic predicate domain we use to infer relations between individual bytes of variables in the two programs, such as those established by bitwise arithmetics. For future work, we plan to industrialize this analysis as a means to address avionics certification objectives related to simulation fidelity. We also want to extend our analysis to further portability properties, such as portability between different layouts of C-types or sizes of machine integers. We also want to analyze software patches modifying data structures, as we think our shared B-cell approach should be successful. Thank you for your attention.